All right, section 8.1, we're going to take a look at simple trigonometric equations. We're going to build off of what we were doing at the end of chapter 7 when we took a look at inverse functions and arc functions, right? They're the same thing, inverse or arc, cosines and sines. Inverse functions allowed us to find the angle once we had a ratio. And we're going to just expand on that. We're going to look at different domain ranges to consider multiple answers for a given ratio value. So here in our first example, we're going to look at what happens if our y value is equal to 1/2. And we're taking a look at our sine curve. And from 7.6, we remember that the angle that produces a 1/2 ratio for an inverse is going to be a 30-degree angle. That fit within our range of our inverse function of -90 to +90. But as we look at the curve for y equals sine theta, and notice that this curve is developed from -2 pi to +2 pi, so we're seeing what we call 2 cycles of the curve. A cycle is a repeated pattern. And so in a sine and cosine world of a parent function, y equals sine theta, which is our parent function, the period, which is describing this cycle, we use capital letter T to describe the period, is equal to 2 pi. That's how long it takes for a repeated pattern, for one of the patterns, and then when we go another 2 pi, you see that pattern repeat. So we're going to actually peek at that stuff coming up here in the next couple sections. But today we're just looking at what happens if I have a y value of 1/2. What we see in this case, we have these 4 locations between -2 pi and 2 pi where my sine curve intersects this horizontal line y equal 1/2. And we're trying to find out what are those angles. Well, we already know one of them is 30 degrees. But where else would I have a positive 1/2 value? Well, if I remember from our acronyms here, where sines are positive, sines are going to be positive in quadrant 1, so I have a theta there, and that's again our alpha, which is our reference angle, in this case is 30. And I also have an angle over here, we'll call that one theta 2, where I have a reference angle of 30 degrees as well. So we said from chapter 7 that in quadrant 2, we know that our reference angle is equal to 180 degrees minus our theta. And in quadrant 3, we know theta minus 180 produces our reference angle. And in quadrant 4, 360 minus theta produces our reference angle. Well, we can use each of those equations to solve for theta instead of alpha. And if we did that, if we knew our reference angle was already 30 degrees, then we know that this theta 2 would be 180 minus 30, or 150 degrees. And that's where that answer is coming from. But if we go the other way, in the negative world, using a 30-degree reference angle, we also have situations where I'm going to have 2 answers, 2 additional answers for where sine is equal to 1/2. And that would be our -210 and our -330. -330 is going around to the left clockwise, putting ourselves in quadrant 4. -210 going clockwise puts ourselves, -330 counterclockwise puts us in quadrant 1. -210 clockwise puts ourselves in quadrant 2, which puts us back at a 30 and a 150 situation for a -210, -330, which is what these guys are. So those are my other angles there. And remember, for sines, if you have a known angle and you want to get back to a place that produces the same ratio value, you can go 2 pi, or 2 times 360 times the number of rotations that you're going to turn, and that will get you the same angle. So this is what we're going to do today. We're going to find these other angles, and most of the time we're going to focus on maybe just the first cycle, the positive cycle of our curve. So in this case, it would have been 0 to 150 for this answer. And that's what this is saying. Again, these can be in degrees or radians, so pay attention. I could also have theta less than 2 pi greater than 0. And that'll tell you what kind of angles you're looking for. All right, so graphically speaking, that's what we're going to be doing. And you can see in some cases, like on our quadrantals, like if I'm looking for where sines are equal to 1, I notice that there are only 2 places that happen, the positive 90 or negative 270. So sometimes we have 2 answers, sometimes we have 4. We're going to see the difference between the 2. Quadrantals are the tricky ones, so just be aware of those angles on the axis. All right, so here we're looking for all positive, notice it's positive angles in degrees for these given trig ratios. First one is a cosine. Remember that we're looking for the angle. We've been given the ratio, so we have our x over r here. And we're going to go ahead, we can use a calculator for this one. That's not one of our special right triangles. So we'd set up inverse cosine of negative 0.6 would produce this theta that we're looking for. Now cosine is the one where, remember, the range of an inverse cosine is 0 to 180, whereas inverse sines and inverse tangents are negative 90 to positive 90. So these answers could produce a theta that's actually not your reference angle. If it's in quadrant 2, it's not going to be your reference angle. If it's in quadrant 1, it is. So if we were to do this on the calculator, it'd be making sure our calculator is in the proper mode. Want to be in degree mode. You would do the inverse cosine of negative 0.6. I get 126.87 degrees. So theta, we'll call it theta 1. Well, we'll call it theta 2 because it's actually in quadrant 2. Theta 2 would be 126.87 degrees. So a little picture of what we have happening here is we've turned an angle this way. We're calling that theta 2. So what we need to find then is this reference angle. So the nice thing about this angle here, this alpha that we're looking for, is again, we're using our rule that the alpha is equal to 180 minus theta. So if we did that, 180 minus 126.87 gives us a reference angle of 53.13 degrees. So our main objective of our inverse is to find these reference angles so that I can put myself in all the appropriate quadrants, whether I'm positive or negative, for a respective trig value. So now that I have this alpha 53.1, I'm going to apply that alpha in the other location where cosine is negative. So remembering all support covers, there's my other location, which means this is my alpha, or my we'll call it theta 3 because we're in quadrant 3. That's my other angle that I'm interested in. And theta 3 is going to be found by 180 plus alpha, or in this case, 233.13 degrees. So there's my other angle. Those are my 2 angles then that produce a cosine ratio of negative 0.6. Both those angles fit between 0 and 360, so we're good. What about a cosecant? Well, the cosecant, remember, is the inverse of a sine. So maybe what we want to do is write this as a sine of theta, and then remember that we just take the ratio value and we write it as a reciprocal. So sine of theta is equal to 1/2. And now what we do is we're looking for the inverse sine of a ratio of 1/2 producing some angle theta. And we know that that happens to be 1 or 30 degrees. Theta 1, since it's in quadrant 1, will equal 30 degrees. And this cosecant value of 2 is a positive, so we know that a positive sign happens in quadrants 1 and 2. Now, because we found theta in quadrant 1, we also know that that is equal to our reference angle. Again, a little sketch. There we are with our angle theta, which is our alpha. Now we're going to apply that angle over here for theta 2 using the same alpha. And if we did that, we get theta 2 is equal to 150 minus, or not 150, 180 minus 150 degrees. So those would be our two angles that produce a cosecant value of 2. All right, what about this next set here? Up until this point, we've just seen, here's a trig ratio, here is the angle. Well, now we have some other things going on. We've got a coefficient multiplying by our cosine value. We've got a constant that we're adding, and then we have our constant on the other side of the equal sign. And what we want to get this to is a situation where it just looks like cosine of theta equals some number. Well, specifically some number over another number, or x over r is what our cosine measures, right? All right, in order for us to do that, we need to, this is like, it's like treating this cosine theta as like an x. That's our unknown. So we have 3 to the x plus 9 equals 7. And how would we solve for that x? Well, we move the 9. And then we have 3 to the x equals negative 2. And then we would divide by the 3. We get x equals negative 2/3. Well, we substituted our x for cosine theta. So really what I have here, and I didn't have to do substitution, just showing you that we're treating this just like any other equation. We have the value of cosine of theta is now equal to negative 2/3. So right here we were letting x equal cosine theta. And again, you don't have to do this. This maybe gives you a different way of looking at it. All right, so this is the case that we have cosine theta equal negative 2/3. I notice I have a negative ratio value, which means I'm in quadrant 2 with this thing. So when I go find the inverse cosine of negative 2/3 to produce my theta, again, it's going to be a quadrant 2 theta, so we'll call it theta 2. I'm going to do inverse cosine of negative 2/3. I'm going to get 131.81 degrees. And then thinking again where you are, over here, 131.81, what would be the reference angle alpha? It would be 180 minus that. So I can say that my alpha is going to be 180 minus 131.81 degrees, or what do we get? 48.19 degrees is your reference angle. Got to go find the other place where cosine produces a negative ratio. That will happen right here. So now I'm thinking about theta 3 as my other angle. We know that theta 3 will be found by 180 plus my reference, or in this case, 228.19 degrees. So there are my two angles that produce this this cosine value, theta, that fits this equation here. What about when you have powers? Well, we want to talk about trig ratios and powers. Cotangent squared theta is actually, what we're doing is we're taking the cotangent of an angle and we're squaring the entire thing. So cotangent theta squared we will write as a power after the name of the function, sine, cosine, tangent, cotangent, secant, cosecant. So put the power after that, and then the theta. So these two are identical, cotangent theta squared and cotangent squared theta. So what we have here is a situation where I need to get rid of that power. And in order for me to get rid of a power, we know that we're just going to take a root. In that case, I get cotangent of theta is equal to plus or minus 2. Plus or minus 2. Well, let's make this become a tangent value. So tangent is the reciprocal of cotangent, which means it's now plus or minus 1 over 2. And then let's go look at this. We got an interesting situation here. We have a positive value of tangent and a negative value of tangent. So first of all, our positive values of tangents. Theta 1 and theta 2, or actually theta 3. Remember, this tells me tangent is quadrant 1 and 3 positively. Where is tangent going to be negative? Because it's a negative 1/2 as well. Well, that happens over here, where theta 2 occurs, and all the way around, theta 4 occurs. So we're going to have 4 answers for this. All right, let's first of all go find our theta as our reference angle. So what we're going to do is we're going to look at theta is equal to the inverse tan, and we're just going to use the 1/2 value. And again, this will produce for me theta 1, because it's a positive ratio. So we're going to do inverse tan 1/2, make it 26.57, we round it, 26.57 degrees, and again, because that's an angle between 0 and 90, that is also our reference. So now it's just a matter of simply going to find theta 2, theta 3, theta 4 by using this reference angle in each of my quadrants. So let's go look at theta 2, which is one of our negative values. Theta 2 would be equal to 180 minus alpha, or in this case, 153.43. I'm doing my math right. What about theta 3? Theta 3 is one of my positive tan values, and that's going to be 180 plus my alpha. So I'm going to have 206.57. And then finally, theta 4, which is a negative tan value, 360 minus alpha. So 360 minus 26 gives me a 333.43. And there are all 4 now values, because I have positive and negative. Those are all 4 of the answers I would have between 0 and 360 for this cotangent squared theta equaling 4. So whenever you square root, because you've got a power on that trig function, you're going to end up with, in this case, 4 answers between my 0 and 360. Okay, let's let you guys try. Here are a couple problems. You might want to pause right here, because I'm going to flash the answers for you real quick, and you can see how you did. So take some time to work it out, maybe pause the video, and then come back to the answers. Here would be your answers. Tangent theta equals 1.8. We're looking for positive tangents. So we do my inverse tan at 1.8, I get 60.95, which is a reference. Add that to 180, quadrant 3, and I get the 240.95. Secant theta equaling negative 2.85. Let's write it as a cosine theta equal negative 1 over 2.85. So I'm looking for quadrants 2 and 3. For sine squared theta equal 1. Well, let's get rid of the coefficient first, divide by 4. Then we will undo the power, so we're going to take square root of sine squared theta, square root of 1/4. I get plus or minus 1/2. And there would be my answers for all 4 quadrants again, because I'm looking for positive and negative values of sine in that case. And there we have it.